Hey everybody, Mr. Judson here. Oh boy, yeah, so we're ready to start talking about related rates. Some people may, as we learn this, go, oh, this isn't that bad. You made it sound like it was scary, Judson. It's like you have to really try hard to understand what's going on. And I think once you understand, it really kind of makes this not too bad, okay? But the idea of related rates, what it means is things are changing with respect to time, okay? As time goes on, things change. An example, if I had a balloon and I was holding an air hose and I was squirting air into it, as time moves forward, that balloon gets bigger and bigger. Its surface area gets bigger, its volume gets bigger. Everything's changing with respect to time. And that's the way we got to think of these problems. So really there's two steps we want to follow. And if we follow these two steps, it's not bad, it's just making sure we understand, okay? So step number one is we want to find the derivative implicitly and then this is the part that's different. Instead of getting all your dx's on one side, dy's on the other, or whatever the variable is, we want to divide everything by dt. Okay? Because what we're saying is things are changing with respect to time. It's kind of like when we say dy over dx, we want to know how is y changing with respect to x. The moment we put a dt in the denominator, now we want to know how things are changing with respect to time. And that's really what related rates are all about. Some of the problems we look at today are going to be they look just like math problems. They're not really going to relate to anything. I think as we start getting into the problem solving end of things, then yeah, we'll start to see how this stuff is being used. Just so you guys know, this is the last section in this chapter, which means we've got an exam coming up. We're going to introduce the idea today, which is Monday. That's it for this week. We're really going to work hard next week at making sure we get related rates on Monday and Wednesday, and then on Thursday we'll review for our exam, which would be the following Monday. So I don't even know what day that is, but that's the plan. All right? All right, let's do an example. So just so we can kind of get the idea of the steps to follow here, if I take the derivative implicitly, I'm going to say the derivative of this is 1, and I just took the derivative of y. This will be 2x, and I just took the derivative of x. And then here I've got a product rule. So I'll take the derivative of the first piece, which is 2, times the second part y, and I just took the derivative of x, plus, leave that 2x the way it is, take the derivative of y, that's 1, and I just took the derivative of a y variable. Okay? And so now my new step is divide everything by dt. So when I do this, what you do to one side, you do to the other. I'm going to assume that this is now a common denominator for all three of these terms. So let me go back and change that. I've got a dt here, I've got a dt here, and I've got a dt here. And so usually what we do is we rewrite that. dy over dt is equal to 2x times dx over dt plus 2y dx over dt plus 2x dy over dt. And so really, I just wrote the same thing twice. What I could have done is let me just go back and erase some stuff here. I could have said, just divide all the dx's and dy's by dt, and now I've got the same thing that's written here. And then usually what happens is they'll say, find dy dt if dx over dt is changing by 3 inches per second. You know, something like that. They'll give us a number to plug in for this. And so we plug it in and then just solve for whatever's left. We'll see that on our next example. But I've done what these steps right here say. I took the derivative implicitly. I then divided everything by dt. And so now what I have is rates of change with respect to time. Okay? Let's see if we can get something that has a little more information in there. All right, so this problem has a little more information to it. They're telling us here's an equation, and they want us to find dy over dt when x equals 4 and dx over dt equals a negative 2 inches per second. So really what they're saying is at what rate is the y value changing at the point where x equals 4 and my x value is decreasing at a negative 2 inches per second. Okay? Now, if you think about this, this is the equation for a circle with a radius of 5. So the idea is we've got this dot that's moving around the circle. Since dx over dt is negative, that means my x values have to be decreasing, so it's on the top part of the circle. It's moving this way. Okay, I guess if the dot's going this way, we're on the bottom part of the circle. We're going off in the negative direction. Okay? And so what's the y value doing when that's happening? Well, if you think about a circle, let me just draw a quick graph here. Here's my circle. I've got this point. If it's moving this way, that's where my x values are decreasing. They're getting smaller. And for part of this, the y values are going to be increasing and getting larger, but then when we start coming down here, my y values are decreasing and getting smaller. So, you know, at the point where x equals 4, we're probably right in this area somewhere, so I would expect my y values to be getting larger because we're heading up on the circle. Okay? Now, even if I didn't understand all that, I could still do this problem. I just need to take the derivative, so that's 2x, and I just took the derivative of x, plus 2y, and I just took the derivative of y, and the derivative of a number is 0. Now divide everything by dt, which really that's going to amount to just the dx's and the dy's. If I divide this by dt, I still get 0. 0 divided by anything is 0. So now at this point, I just want to plug in the information they gave me. Okay? X equals 4, so I've got 2 times 4. Dx over dt, it's decreasing, so negative 2. I've got plus 2, and what's y equal to? They didn't give me that value. And I'm trying to find dy over dt. This is what we're solving for. So I want that to remain a variable. I just need to know what this is before I can move forward. Well, the thing about these kind of problems is there's always going to be a way to figure out what y is. We just got to find that way. And the easiest thing is just to take 4 and plug it back in here and solve. Right? So if I plug a 4 in there, I get 16 plus y squared equals 25. I'll move that 16 over and subtract it. I'm going to get 9. And then if I take the square root, I get y equals plus or minus 3. So when x equals 4, I could have a positive 3 or a negative 3. And if the point's going this way, then that means for x to be for my dx over dt to be negative, I've got to have my x values getting smaller. Okay? They're moving to the left. If this point was down here, then it's moving to the right. Now here's the thing. I don't really know which way this point is going as it rotates around the circle. It's just traveling around the circle. I don't know if it's going counterclockwise or clockwise. They didn't give us that information. So maybe that means there's 2 different answers to this. So let's see, if I plug in a 3 first, I've got 8 times a negative 2, that's a negative 16. plus, if I put a 3 in there, I've got 6 dy over dt, that equals 0. I'll move this to the other side. I've got 6 dy over dt equals 16. Divide by 6, I get dy over dt equals 16/6, which reduces down to 8/3. Now what if I would have put a negative 3 into there? Well, let's see, that would have made this negative. I'd still move that over. It'd become positive. This would still be negative. I would divide and get a negative value here. So really my answer is plus or minus. Right? So if I go back and say this right here could have been plus or minus 3. So now that makes this plus or minus 6. So now when I move that over and divide, I get plus or minus 8/3. There's my answer. Oh, almost. Inches per second. Got to make sure to include that unit. You've got to have units with related rates. Those of you who want to take the AP test, extremely picky. Every time you leave the units off, automatically minus 1 point. Got to include the units. That's a big deal. Okay. All right, let's try another one. All right, so y equals 1 over 1 plus x squared, and they want us to find dy over dt when x equals 2 and dx over dt equals 2 centimeters per second. So before you take the derivative of this, remember that one problem we had where there was like a fraction and we said, oh, this will be a lot easier if I just take it over here and multiply? Rather than doing the quotient rule, bring this over here and then do a product rule, and I think we make this a little bit easier. All right, you guys go ahead and try it. All right, so if I rewrite this, y times 1 plus x squared equals 1. I can even say y plus x squared y equals 1. Now I'm ready to take the derivative. So derivative of that would be 1, and I just took the derivative of y, plus, I do a product rule, so that would be 2x times y, just took the derivative of x, plus x squared, derivative that's 1, just took the derivative of y, and that equals 0. Divide everything by dt. Divide this by dt, I still get 0. And now we're ready to plug numbers in. So when x equals 2, so I got to figure out what y is when x equals 2. So I'll just do that over here. Y equals 1 over 1 plus 4. There's my y value. So we're trying to solve for dy over dt. Now this time we have 2 of those. Okay, so we're going to have to figure out how to get that by itself. But let me plug in numbers first. I've got dy over dt plus 2 times 2, that's 4, times 1/5, that's going to be 4/5, times dx over dt, that's 2, plus x squared, that's 4, dy over dt. Equals 0. So what I want to do is I want to factor a dy over dt out of both of these. So what I get is dy over dt. Factored out of here, you're left with 1. Factored out of there, you're left with 4. And that equals, I'm going to move this to the other side and do the opposite. So what is that, 8/5? So when it goes to the other side, it becomes a negative 8/5. This equals 5, all I got to do is move it over and divide by 5. Okay, which when you divide a fraction by a number, what you do is you just multiply it right into the denominator. Right? If I come over here and go a negative 8/5 divided by 5, which would be 5 over 1, I got to flip this over and multiply, and so that 5 just ends up right in the denominator. All right? So that means that dy over dt is going to equal a negative 8/25 centimeters per second. There's my answer. If you're sitting there going, what does that even mean? Well, whatever that graph looks like, if we've got a point moving along the graph, and I'm at the spot where x equals 2, and my x value is changing at this rate, well, this is the rate at which the y value is changing. This is a really different way of thinking. I mean, none of us have ever looked at a graph and said, God, you know, if there was a point moving along that graph, and the x values were changing at this rate, I wonder what the y values would be changing. You know, no one's ever thought that before. Well, none of us have thought that before. Plenty of mathematicians have. So this is a new kind of thinking for us. All right? Let's try another one. All right, I love this problem. At what rate is the area of a circle changing when the radius is 6 inches and dr over dt equals 4 inches per second? So, have you guys ever been like at a lake or something and you throw a rock in the water and it splashes, but then you see these ripples, they get larger and larger and larger. Don't tell me this thought didn't come into your head at that moment, right? But it's kind of what this is talking about, right? You throw a rock in there and you kind of watch the ripples, and what it does is it makes a circle and it gets bigger and bigger and bigger. And so how big is that circle, or how is the area of that circle changing when the radius gets to a certain size and the radius is changing at a certain rate? You'll never throw a rock in the water and think the same way again. Well, let's see. At what rate is the area of a circle changing? So whatever question they're asking us, the rate of something, I need to start with an equation about that right there. So if we think, well, how do you find the area of a circle? It's area equals pi r squared. That's what I need to take the derivative of. This is good. We're actually getting into a problem that has some meaning to it, and we'll get into plenty that have lots of meaning to it. But this is a pretty good start. Okay. So if I take the derivative of this is 1, and I just took the derivative of a. Pi is just a number, so there's no product rule here. When you take the derivative of this, I get 2 pi r, and I just took the derivative of an r variable. Whoa, I just thought of something here. Remember how, there's area and there's circumference, and for some reason we always have a hard time remembering the two? And area equals pi r squared, and circumference equals 2 pi times the radius. Circumference is the derivative of area. What's kind of interesting is if you think of a sphere, the surface area of a sphere is the derivative of the volume of a sphere. Look it up. Look up surface area and volume of a sphere, and you'll see that the surface area is a derivative of that. So that's kind of weird. I mean, for some people, that almost helps them keep those two straight at this point. We don't mess up on the formula anymore because we start thinking derivative. All right, so let me get rid of that. So now I need to divide everything by dt. So divide by dt, divide by dt. There's only one term here, so I only do it once. And now plug in the information. So dA over dt is equal to 2 pi times the radius, which is 6 inches, times dr over dt. So this is increasing at a rate of 4 inches per second. So how is the area changing? 12 times 4, that's 48 pi. This is area. So area is measured in square inches per minute. Is that per minute? Per second. Oh, yeah, per second. So square inches per second. That's the rate at which the area is changing. I always found this to be a really interesting problem, because if you think about lumber, okay, I know this is weird, but bear with me. If you think about lumber, and I've been around longer, so I realize this. You used to see a logging truck go down the road, and 3 logs, huge logs on the truck. That's all it could fit. Nowadays you see a log truck going down the street, and there's like 30 logs, 50 logs, and they're all like this. They're little tiny trees. Why are we doing that? And so I thought about this one day, and I thought, if you take a tree after it's been chopped down, we all know that there's rings in there, and you take all those rings, here's the center. There's a growth rate to a tree. And some rains are bigger than others. Usually that means there was a really wet year, and so lots of rain, so the tree grew quite a bit. But for the most part, those rings are all about the same size. And so there's a rate at which that radius is growing. And if you think about what we just did right here, as that rate would probably be the same, but as the radius gets bigger, it means that the area of that cross-section of the tree is growing exponentially, right? Because we're squaring it. So the longer you let a tree live, the more and more lumber is produced. So rather than cutting down these little tiny tadpole trees, if we just let the tree go and let it go, and it gets bigger and bigger and bigger, it starts growing faster and faster and faster. The amount of lumber you get out of it grows exponentially. And it's not just the cross-section of the tree, it's getting taller as well, right? So, kind of a fascinating thing. I find myself wondering, has the lumber industry ever talked about this? Have they ever done the math? Or do they just go out, no, it's a chainsaw, man, cut down a tree. There's got to be somebody in there that's smart enough to understand that. So yeah, in my mind, it makes sense to leave trees longer, because the longer you leave them, the more lumber you can get out of it. Exponentially more. So it's not like if I let it go twice as long, I get twice the wood. No, if I let it go twice as long, I might get 30 times the wood out of it. Interesting thought. All right. All right, that's as far as we're going to take this for today. So let me get you guys a homework assignment. All right, so we've got assignment number 11. This is week 11. This is the only assignment for this week. Page 157. We're going to do 3 to 10, part A only. There's like an ABC. Just do part A. Okay? And then we're going to do 12 to 14. All right, that's it, you guys. I hope you have a good Thanksgiving. Stay safe. Enjoy time with your family. Bye.